Introduction. Hello, my name is Alberto Sonnino from UCL and also one of the co-founder of ChainSpace. This is joint work with Professor George Danezis, which couldn't be here today, which is also from UCL and one of the co-founder of ChainSpace. So among all the possible challenges that we may have on blockchains, here, this talk would focus on how to build strong sybil resistance. So, particularly, we will consider a subset of the problem, which is how can we bootstrap a federated Byzantine agreement system in a sybil-resistant way. So imagine that we have, as a general setting, all of those nodes here. So the nodes don't have to be known in advance. And what they do is that in some ways they choose which other node to trust, and they create those links between each other. So they would create some slices. And the question is, can we actually achieve that setting here, so those quorum slices in a federated Byzantine agreement system, with a strong sybil resistance way? And so this is the question that we're trying to answer today. So first of all, very quickly, what are the sybil attacks? I'm sure everybody knows here what they are. So imagine that you have a classic BFT setting like this one, where we have so the three green nodes which are honest, the red one which is dishonest. And if you go from this to an open system, well, there is obviously nothing that prevents the adversary from replicating himself, creating many fakes identity, and potentially take over the system. And so the traditional way we handle these kind of problems is by capping the adversary ability to create many fake identities. And there are many ways of doing this. So traditional defenses, which involve, for instance, proof of work or proof of stake, will try to leverage some scarce resources in order to make it work. So the idea is they want to cap the adversary ability by leveraging scarce resources, which is, in this case, we can see it as money. Right? If we leverage money by forcing the adversary to burn or to lock some of it to participate in the consensus, well, it means that it's not free anymore for the adversary to create many fake identities. And this is what it would look like. So now, each time that a new node in the open system wants to join the consensus, well, it would need, for instance, to lock some money just to participate in it. So you can see that the adversary, the red one here, can still replicate himself if he wants, but he needs to be rich because he needs to lock a lot of money out. And this works quite well, but sometimes it's not enough. So here, to illustrate why, we take a very extreme example, which is a company called Vega, which does decentralized trading of financial products. So what it does is every transaction on the system has a potential real big deal in terms of real world value. So it can represent some transactions which are financial products, potentially very expensive. And so this attack can become very real, right? So step one is the adversary would borrow some money to a bank, then turn it into token, use it to create many fake identity, but knowing that the transaction have a lot of real world value in that particular example, well, it can extract some money out of it by subverting the system, pay back his loan to the bank, and still be financially winning. And so what we're trying to do here is to see if we can strengthen the existing mechanism. So if we can have something a little bit more than what is traditionally done. So leveraging scarce resources is still the key idea here. We still keep leveraging money as one of those resources. We still want to force the adversary to lock or burn a part of it. But we had a new thing here, or at least in this concept, is that we also leverage trust, which is a new kind of scarce resource here. So we leverage this by penalizing poor judgments between nodes. And this is basically the core of how SybilQuorum works, and this is what we're going to talk about today. So I promise to keep the talk short, as it's the last one of today. But this is generally how it would work. So SybilQuorum has two components. The first is traditional proof of stake. We don't innovate much here. And a social network analysis. And we bring the two together. So what we do in the term of proof of stake is the first thing I will talk about now. Instead of locking some stake for yourself as a node when you want to join the network, you would lock the stake toward a particular link for another node. And then we use social network analysis to have a view of sybil regions on the network. And so here we see how to go, right? The question is from the start, how can we bootstrap a federated Byzantine agreement system using SybilQuorum in a strong sybil-resistant way? And we can go in 3 steps. So step 1, we need to attribute weights to the nodes that we trust, right? So imagine that we are a node, we check the other node that we trust, maybe we know them personally, maybe they're trustworthy organizations, and we attribute some weight. So this is how we would do. The goal is to have a stake-weighted trust relationship graph. This is what the node's view of the network may look like. So this is the connection it knows, the one that it sees through the network. And what it does is that it will lock money on the links with other nodes. So it does it in a very particular way, because the protocol would say that once you lock your money to a particular link, any vertices of the link can withdraw the money, take it out, and add it to its account. And so this is the key idea on how we leverage trust and we punish poor judgment of nodes. Because imagine, obviously, that a node would put some money on a non-trustworthy node, like a fraudster. The first thing that would happen is that a fraudster node would simply take out the money of the link and disappear with the money. And so the idea that we have around this is to say that bulk dishonesty would protect against strategic dishonesty. So imagine that we have that very rich adversary, which creates a lot of sybils and then would put a lot of money between the links on the sybils. Well, now, if you're a honest node, you will be super careful before putting your money on the link with someone you don't know. Before you could, right? There was nothing really preventing you. At the end of the day, it's just about running consensus. You won't be impacted directly, or at least on the short term. And now we hope that nodes would be much more careful, and therefore the links toward these malicious regions would be more rare. And so this is step 1. So step 1, we attribute weights, you lock stake on the links of the nodes you trust. So now step 2. Step 2 is we run a social network analysis. So this relies on the fast mixing assumption. And the idea is to say, let's imagine that the network looks like this. So this is a very idealistic attack where we have a lot of very well-connected sybil region in gray on the slide. And then you have the normal network with all the nodes, the honest node, let's say, or potentially some of them are dishonest, but they're not making the sybil attack in green. So the fast mixing assumption says mainly 2 things. The first is that if you're a node, so not an army of bots that wants to join the network, well, you will integrate into the network quite fast. And it will be a slow integration of the huge part of the sybils connected between each other to the real network there. So we assume that people won't specifically trust bots, and if there are a lot of them, they may take time to be included in the network. So this is an important assumption that we use here. And so step 2 would work as follows. So first, each node performs a local judgment. Each node takes its own view of the network and input this into a black box algorithm. So this black box algorithm is the social network analysis. I'll come to that in a moment. And the output of that would be a map between all the other nodes that the node running the algorithm put in, with a map which represents a probability of the node being a sybil or a node being honest. So let's say that the higher that value is, the more probability you have to be an honest node. And this black box, in our case, is sybil-infer, so the first here. So you may be familiar with that, but I mean other examples exist like sybil-guard or sybil-limit. So in the interest of time, I won't explain how sybil-infer works here, but a general idea is that if you start from an honest node in green here and you take short random walk through the network, well, you have higher chances to end up on a region of honest non-sybil nodes of non-sybil nodes, actually. So if you start on the sybil region, you will take your random walk and with higher probability stay in the sybil region. And this is due because since there is a cut on the graph, well, you can distinguish statistically the random walk regions. So once you do that, what you would do is you can define a Markov chain, and if you choose your distributions right, you will have a nice transition matrix. So, but I'm happy to chat about that after the talk if you're interested in that. But basically what happens here is we reuse sybil-infirm almost as it is. We just modify it a little bit to make it work with weighted graphs, while the original paper explained how to make it work for non-weighted graphs. Okay, so step one was we attribute weights to our links. Now we have a stake-weighted trust relationship graphs. We use it as inputs to run a social network analysis using a slightly different version of sybil-infer. And now the third step is we try to determine the quorum slices out of it. And so this is how we would do it. So each node, it has an input. It now has as output the map between all the other nodes and a weight. And it would check and select a threshold value y here. So in the paper, we explain how to define in a nice way those value y, but basically it's a threshold value here. So what it does, it will select all the a set of all the nodes that have a weight bigger than the threshold value, and all subsets, which are 2/3 of the number of the size of the set, will actually become one of the quorum slice of the nodes. And so that's it. Those are the 3 steps to bootstrap an FPath using SybilQuorum. So the first, the sybil weight, the weight, then you have that mapping functions, and then you use the idea of the cutoff threshold value to create the quorum slices. So this is what we are up to now, and we still have to evaluate the system. So this is work in progress, actually. And what we want to do is to evaluate those 4 things mainly to see how well we perform and if it could be used in practice and in which scenario. So the first thing to see is what happens and how the system behaves if you modify the number of sybil's nodes. So if the gray region becomes a lot bigger. And so this is relatively cheap for the adversary at that point. But then the test would be what happens if you increase or decrease the stake that the adversary can put on those links. So how rich is the adversary? So how this would influence the system, basically. Step 3 would say, what's the number of link between the honest nodes and the sybil region? So those would be actually naive nodes that get confused and link to the sybil region. And then how many of those connections we have, of course, because this would influence the social network analysis. And so that's it. So in conclusion, SybilQuorum, it's a sybil resistance mechanism here. So what it does, it leverages money by forcing people, nodes to lock it or to burn it, as in traditional proof of stake. So instead of locking it on for the node itself to enter the system, it would lock it into some links. And the second thing it leverages is trust by penalizing poor judgment, because of if you connect to a fraudster, where he could simply take out the money from the link and disappear with that. And so how we do it, using traditional proof of stake and the weighted graphs, and social network analysis to determine the sybil regions probabilistically. Thank you for your attention, and if you have any questions.
Okay, let's thank the speaker. Do we have questions? Yes.
Thank you for the talk. This is a fantastic subject to me, very interesting to me. So I'm still trying to understand it, but let me give you some of my daily life example to see if address this.
Absolutely.
For example, first, I think one of the fundamental element of this algorithm or protocol is rely on the trust. My question is, how do you know that one is trust? How do you trust that is trust? Right? The biggest enemy is the one you trust.
Exactly.
That's how do you trust? How do you determine the trust? When you have a spy here, you trust him more, you're more in danger, right? In the reality. Second part on the money side. In the reality we have seen in the true world, And lots of the hackers, they have lots of money. And it's not from their money. They steal multi-layers. For example, they stole lots of credit cards. Funding the money from the stolen credit cards, they have tons of money. So we always view their true enterprise customer or whoever that customer is, because they're funding, they're paying the bill in the Amazon, wherever that is, they leverage the resource. How do you deal with that in this algorithm, that they do have the money? 2 questions from me.
Yes.
So it's very fascinating subject to me. Yeah, I'll talk to you more probably after this one as well.
Thank you. So yes, actually, those are good questions. So the idea here is that self-imposed vulnerability would imply trust, right? Because if you choose yourself to trust someone, so you should probably know in real life, because I won't trust a bot with my money. I mean, I would if I didn't have to pay and there was no risk for me to lose anything. But in that case, we would assume that, as in the original FBAS definition, you would simply have arbitrary judgments. Well, here, you would need to see them in real life. So this is, we don't do it, we do it offline, let's say. This is how you know that you trust somebody.
As a system, right? So one guy maybe original is good, you trust, but they may be converted to a spy.
Oh, yes.
Or someone hacking the system too.
Absolutely.
How do you trust that trust? That is the
Absolutely.
fundamental question.
Yeah, I mean, that's as good as it gets, right? If you trust somebody, you put some money on there and it get hacked and you take your money, well, that's unfortunate. But that's an improvement over traditional proof of stake. That's how good it gets, absolutely. So yeah, I'm happy to chat more about that, but I think that we are hitting here a limitation of the system more than anything else. And what was your second question?
Why don't we take the second question?
Absolutely, yeah.
Yeah, thanks. You mentioned about fast mixing as one of the assumptions, but after all this sybil limit, sybil infer paper came up, the studies showed that social networks as well as networks for financial networks are not fast mixing, at least in current form. So do you guys have some thought in that respect, that you see, no, indeed, you are going to see that fast mixing assumption is going to work for you?
Yes, so we have a slight discussion about that in the paper. We're well aware that most of the network are not fast mixing in the sense work. So this is an assumption that is needed for to determine the cutoff regions, and we think that we leverage this and make it a little bit better by the way we select that threshold value. So I didn't have time to say how we do it, but there is a paragraph in the paper that explains a little bit more about that. So since I see that there are other questions, maybe it's...
Where is the paper?
Sorry?
Paper?
Where's the paper he has?
Oh, yes. Yeah, I mean, I would send it to you. I'm not sure we put it on archive yet, but yeah. I can chat about this more offline because it involves a little bit more explanation to say how we get those regions.
Quick question about incentives. Do you naturally assume that honest participants want to grow the network? Because it would seem to me, if I'm an honest participant, I don't necessarily have any personal incentive to extend trust out. And so how does this system handle that?
So that's a good question also, right? Because what would happen is you have an incentive to join the network and to grow the network, because that's how you participate into consensus. If you lock more stake in a traditional proof of stake system, you may have more chances to be selected to participate to any committee and earn rewards from transaction money. And here, the way that we would select the transaction committee would depend on the number of connection you have in a weighted way with respect of how much stake you put on it. So there is an incentive, the same incentive that you have to join the network. Actually, you have the same in having a lot of good relationship with a lot of stake on it. And also, the thing that I didn't mention, the protocol leverages the fact to have reciprocal relationships. So if I'm someone that trusts a lot of people, but no one trusts me, so this will also impact me in a bad sense. But yeah, this is also something I didn't mention, so it's a good question.
This is a very interesting idea. I have a quick question. So we assume here every node is either good or bad, right? So what happens if a node is classified to be honest, but later it turned out, once he classified to be honest, he's gonna do malicious thing. So how do you,
Yes, so maybe I use a slightly confusing terminology here. So we need to bootstrap the system and we try to avoid sybil nodes. So we assume that a node that has a lot of fake identity connected to each other, but not connected into the real network, are actually simply bots or something like this. So this is what I mean by bad node, because out on top of it, you would run your federated Byzantine agreement system, which is fault tolerance in its own way, depending on the system and whatever you run on top of it. Does it answer the question?
Okay, that closes the sessions for today. Do we have any, what? We have, do you want to take over? Let's have a message from the...
Well, we have a reception, which I think starts outside, and there's drinks and food and time to